to make sure we are recording. Huh?
You are.
I am? Okay. I'll take your word for it.
I think it's just screen sharing. Oh, the little dot is blinking though. Doesn't that mean record?
Mm-hmm. Yeah, I think you're right. I think it does. Cool. All right.
Oh, there. Got it.
It's like way up there.
All righty. I think we're ready to go. I think this is the last slide I showed last time, where we're just making or reiterating the point that when we reach an electrochemical equilibrium in the cell, this kind of illustrates kind of what's going on here. In the case of the flux of sodium and potassium in and out of the cell, we have that sodium-potassium ATPase, which is actively transporting 3 sodiums out, 2 potassiums in, and this is creating a gradient for both of these ions. And the gradient, it gets sufficiently large where we end up getting some leakage of sodium back into the cell, potassium back out of the cell through passive ion channels that exist in the membrane. And at some point, the chemical gradient and the electrical gradient, we've talked about this before, are going to come into balance such that the flux of sodium potassium will reach an equilibrium, and we will have no more net flux of sodium or potassium in either direction across the membrane. We all get that? Okay, cool. All right, we're going to start to define a couple of terms. If the membrane potential becomes more negative, then the cell is said to be hyperpolarized. And this is more negative relative to the resting state. Okay? Likewise, if the membrane potential becomes more positive, then it is said to be depolarized. And that word depolarized gets very important when we start looking at action potentials, because that's the big event in an action potential, is the depolarization of the membrane. All right? And then another term that I will throw in here is that once a depolarization occurs, and then the membrane is going to return, usually towards its resting potential, so it's going to polarize again, we call that a repolarization. So those are just a couple of terms that we will throw around going down the road. Does that all make sense to everybody? All right. So we've been mentioning action potentials for a couple of lectures now, and so we're going to start to actually look at what makes an action potential tick. Membranes of excitable cells, when they become sufficiently stimulated. Sufficiently stimulated means that the membrane is going to depolarize past some threshold potential. Okay, so on this graph right here, we have membrane potential on the y-axis, and we have just a time course on the x-axis down here. We see that a stimulation is applied, and the membrane potential is going to increase. Now you see this first dotted line right here, where I have threshold potential in a red box. If the membrane potential exceeds that, all right? If the membrane potential exceeds that, then if this is an excitable cell, an action potential is going to occur. And the action potential occurs because the membrane dramatically increases its permeability to sodium. So, you've got the sodium-potassium pump that's created this mega sodium gradient. All kinds of sodium on the outside, not very much on the inside. When the membrane potential passes that threshold, then the membrane just becomes incredibly permeable to sodium. The sodium just rushes inside the cell and rapidly depolarizes the cell. Not only does it depolarize the cell, the membrane potential is going to exceed 0. In other words, membrane potentials are normally negative. Remember that from last time. They actually will overshoot the 0 point and become positive. This is actually a form of positive feedback. because the more depolarized the membrane gets, the more rapid sodium flows across the membrane. And we'll talk about the dynamics of that over the next several slides. Okay? Now, this increase in permeability to sodium is all about the voltage-gated sodium channels. And I thought we'd take a little bit of time to talk about how these channels work, because understanding how they work is really important to understanding the dynamics of an action potential. The voltage-gated sodium channel is somewhat is interesting because it actually contains two separate gates. And this diagram here is way overly simplistic, but it serves to illustrate how the sodium channel functions. So if we start here in the resting state, okay, and that is the first diagram on the top left here, and it says polarized membrane above it. What you see is there's both an outer gate that is on the extracellular side of the channel and an inner gate on the intracellular side of the channel. Now again, that's really not exactly the way that it's set up, but it works well for illustration. In the resting state, the outer gate is closed, the inner gate is open, all right? But regardless, because the outer gate is closed, the channel is blocked. So no sodium can flow through it, all right? So this does not participate in the flow of sodium across the membrane in the resting state. Now, when the membrane becomes depolarized due to some sort of a stimulation, then what happens is this outer gate will open up, opening up the channel, and then sodium is going to flow through. This is what happens during an action potential. And actually, this is what will happen even during a stimulation leading up to the threshold potential. And one of the things I guess I'll mention here is that some sodium channels will open at a lower level of depolarization than others. So you're going to have some of these voltage-gated channels, and maybe some channels that are gated in other ways that will open up, that will depolarize the membrane a little bit. But once you pass the threshold, you just get this massive opening of these voltage-gated sodium channels here. All right. So the sodium is rushing through, the membrane becomes depolarized. Okay. Now, once the membrane becomes depolarized, and then overshoots zero and membrane potential actually becomes positive, then what this triggers is a closing of the inner gate of the sodium channel. So the outer gate is still open because the membrane has been depolarized. Remember, this is a voltage-gated channel, so it's responding to changes in voltage. But the inner gate, once it gets to a certain level of
The audio cut out again.
Test. Can you hear me?
Yep.
Okay, let's see. I've got a cable problem here. I think I'm gonna have to get some new cables. Hopefully it will stay intact for the balance. Okay. How much of that did you hear? Those of you on Zoom.
The last thing that I remember was the depolarization and the other one like closed.
Okay, so what we've, just to briefly recap here, we've talked about how when the membrane depolarizes, that outer gate is going to open up, okay, and that's the diagram on the right side of the top. down here where it says depolarized membrane. And then once the membrane becomes maximally depolarized, it passes zero and membrane potential actually becomes positive, then the inner gate closes, okay? This inner gate closes, inactivating that channel, okay? So even though the channel is not working at this point, it's still not an arresting configuration. But it's important that the channel stop working here, because at some point the ion gradients have to be reset before the cell can return to a true resting state. And what we will see in a few moments is this is where potassium becomes important. But we'll get to that in a moment. Yes?
So on the graphic, it looks like the positive charge is like attached to the gate on the first polarized. And then it moves and everything opens, and then because it's moved, the bottom gate can close. Is that accurate?
I'm not sure I really understood your question. These gates are opening and closing due to changes in membrane potential.
Yeah.
So the membrane potential depolarizes, that causes the top gate to open.
Is it just the charges on either side of the membrane, or is there like a proton attached?
It's the potential difference across the membrane.
Okay.
Okay.
So there's nothing like.
So in the resting state, the outside of the membrane is positive, the inside of the membrane is negative. Once the membrane becomes depolarized, that kind of flip-flops. That's why you see the negative on the top and the positive on the bottom in both these other two diagrams here. And when the membrane becomes, totally depolarized, then that total reversal membrane potential will cause this inner gate to close. Okay, and so that stops the flow of sodium at that point, and the action potential is basically done. All right, and now once it's in this configuration, the cell can start the process of resetting the ion gradients to where they are supposed to be in the resting state. Did that answer your question?
Kind of, yeah.
Okay. Yeah.
How does it initially depolarize to the threshold potential if the gates are closed until you get to that threshold?
There's a lot of ways that can happen, but it could be a result of some passively gated channel. So for example, if you have a sensory receptor gets stimulated somehow, that will cause a flow of sodium into the cell. And so it could be another set of gated channels that are ligand gated, that are physically manipulated. They could be chemically gated. Well, that's ligand gated, but it could be a variety of things. It could even be some of these electrically gated channels that are tuned for a little bit lower level of depolarization. But the idea is, and we'll talk about this when we get to the next topic. We'll talk about the importance of the size of that stimulation and how all that's set up. Yeah.
On the polarized membrane, one of the green proteins has the positive right below it, and the rest don't. What is it?
In these two here, you mean the depolarized and the inactivated?
On the polarized membrane one, the protein on the right, the green protein has a positive on the bottom of it.
Oh, on the bottom?
Yeah.
To be honest, I'm not sure.
Okay.
I am not sure why.
Okay.
I'm going to make a wild speculative guess here. It's possible that there is an exposed positive charge there that is keeping that gate open. That's a possibility, but I don't know that for sure. Yeah.
Kind of off of Carl's question. Why would you need this like extreme depolarization that shoots it above the threshold if there's already passive transfer over the membrane?
Well, because all that does is gets it above the threshold. The membrane potential is still very negative at the threshold. So if we go back to this diagram here, if the threshold is along this dotted line here, it's labeled threshold potential right here, you can see that that's still very negative. And so at that point, the voltage gated channels just haven't opened up. But once they opened up, you have all those positive charges that rush inside, and it reverses the polarity in the membrane. Okay. Did that answer your question?
Yes.
Anything else? All right. We're going to switch gears here for a few minutes and talk about equilibrium potentials and some theory associated with how they are calculated. And to set that up, we're going to talk about equilibrium potentials, and we're going to focus just on potassium here for a moment. And this slide should be pretty much review for you, and the only point that I am making with this slide here is that you reach an electrochemical balance with every ion, and like I said, we're focusing on potassium on this slide here, where you have the sodium-potassium pump that's pumping potassium into the cell, creating a gradient, a potassium gradient, and then potassium is going to leak out of the cell through passive ion channels until an electrochemical equilibrium is reached, okay? And once you reach the point of that electrochemical equilibrium, then there's not going to be any more net movement of potassium. These next two slides just illustrate that in a little different way. When the cell is not in equilibrium state, you have the sodium-potassium gradient, which has created that gradient, that potassium gradient, and then the potassium is going to leak out of the cell. The key thing here is the chloride stays behind. And so that actually serves to make the inside of the cell even more negative. All right? And then over time, the electrical gradient and the chemical gradient will come into balance with each other. The electrical gradient will begin to pull more potassium back into the cell, because remember, positive is going to move towards negative. And at some point, you reach an equilibrium where there's no net movement of potassium. We all understand that, correct? Shake your head up and down if you do. All right. Okay. So when this equilibrium is reached, we call the potential across the membrane, we call that an equilibrium potential. It's designated by the letter E. You can actually calculate the contribution of each ion to the equilibrium potential. So you can calculate a value for equilibrium potential for individual ions. And so we can calculate this for K. And it would be designated E sub K. All right? And you can do this individually for sodium, you can do it individually for chloride, and here are some typical values for the equilibrium potentials associated with each specific ion here. And these, knowing what the individual equilibrium potentials for these ions are is useful, because these equilibrium potentials put boundaries on the membrane potential during an action potential, and I'll show you a diagram that illustrates that. Puts boundaries on it in terms of how high or low the membrane potential can get. Okay, so how do we figure all these out? Well, there is this fellow by the name of Walter Nernst, who back in the early 1900s was messing around with gas laws and figured out a way to use gas laws to estimate or calculate what the equilibrium potential of a membrane would be. He actually won a Nobel Prize for some of the work that he did. And, you know, this is something that's happening back in the 1920s, so this is something that's been around for quite a while. So here is the Nernst equation. Those of you who've taken neuro have probably seen this before. So, and this is a Nernst equation that's written specifically to calculate the contribution of potassium to the membrane equilibrium potential. So E sub K is equal to R, which is the gas constant, and here's the value for the gas constant, times T, the temperature is in degrees Kelvin, over Z, which is the valence, and the valence is pretty much always going to be equal 1, because all the ions that we deal with for calculating equilibrium potential are single valence ions. And F is the Faraday constant, okay? 96,500 coulombs per gram, and I'm sure you all were dying to know that, all right? Okay, this is times the natural, whoa, back up. This is times the natural log times the ratio of potassium outside the cell relative to the inside of the cell. That's the equation. Okay, now, I will say you can use this equation to calculate the contribution of single ions, such as in this case potassium, to the equilibrium potential of the membrane, or you can calculate all of the ions together. And so when we get to the Golden equation in a moment, you'll see that that's set up to include potassium, sodium, and chloride. So you can add them all in here. You just add them all together. You just add them, you just plus sodium plus potassium plus chloride after the potassium here. But I'll show you that. You'll see how that's done in the nurse equation or the Golden equation when we get to that. Okay. So in this slide, I'm gonna let you in on a little simple secret. All right. This slide is pretty busy, but there's some very useful information in here. This slide illustrates a calculation of E sub k. All right. But it shows you a little trick. If you are making this calculation for cells inside of a human body, where the body temperature is 37 C, the value of RT over FZ can literally be boiled down to 61. So if you ever got asked a question, hint, hint, that involved the Nernst equation, or when we look at the Golden equation, the same thing, for something happening in a human body, you can take that whole front term and boil it down to 61. There is one other little change you have to make to the equation though. So you'll note that that's what they have done in this example. So it's E, this is actually E sub k, is equal to 61 over Z. Z's always going to be equal to 1, so we get rid of that. But note that instead of the natural log, we've converted to log base 10 here. All right? And then we just multiply that by, we just take the log base 10 of the ratio of potassium on the outside relative to the inside of the cell. Now, the reason, the constant of 61 here, where we get that from, is it's basically RTFZ times the value of 0.2303. And where does that come from? If you look in the blue in the upper right-hand portion of the slide here, so I told you there's a lot of good useful information here. We can convert natural log to log base 10 by simply, or we can use log base 10 by simply adding this constant of 2.303, multiplying that by the log base 10 value of it. And so this constant of 2.3003 here is folded in to this value of 61. So in essence, it's going to be this at the very last point on the slide here, 2.3003 times RT over FZ, and just multiply that by log base 10 times your isotope ratios. Does that make sense to everybody? Because I am not a math teacher, and I feel like I just really rambled through all of that.
So is it, so I guess what is the 61 in retrospect to the 2.303?
Well, the 61 is a constant that is calculated as 2.303 times RT over FC.
RT over FC times 2.3 equals 61.
Equals 61 for something being done in a human. In other words, when the temperature is 37 degrees
With those
C.
variables, okay.
Yeah. Now, if the temperature is something else, that value is going to be something other than 61, and I'll illustrate that when we get to the Golden equation.
Okay, thank you.
Does that make sense?
Yes.
This is just a little simple thing. If you're working with humans, you can skip the whole RT, FC, just change it to log base 10 and stick 61 in front of it, and you can do the calculation. Yeah.
So is all of this just getting everything in the same units? Is that what happened?
Actually, when this is all calculated, it actually comes out this actually will calculate out into volts, and we want millivolts, which is the first note that I have here in red,
Yeah.
where it says RTFC is in units of volts. This is a ratio, so it's unitless. The ion concentrations are a ratio, so it's unitless, but the RTFC is in volts, and so we want it in millivolts, so we just multiply it by 1,000. So if we didn't multiply this, they've already multiplied this by 1,000, and that step is actually not shown here. But it's minus 90 millivolts, but it's 0.09 volts. Or is that right? Yeah, it's 0.09 volts.
So 61's already in millivolts.
No, actually, no, it's not. I don't think so. You know what? I would have to punch numbers, but I don't think so, because I think this has to be multiplied by 1,000. And I'm actually, now that you've asked the question, I'm not sure if that's done in the calculation of 61 or not. You could run the numbers and see. It'll be easy enough to do. So I can give you all the values for RT and F.
Just want to make sure, in the off chance that there happens to be one on the exam.
Well, you will know, when you run the calculation, you'll know whether it's in volts or not. Because if you get a value that's 70 or 80 or 90 in there, or even 40, you know that's going to be millivolts. Otherwise, if it's going to be in volts, it's going to be 0.0 something.
I think 61 is already in millivolts.
Okay, that's possible. You know, when she asked the question, I actually wasn't sure whether it was folded in or not, but that's very possible that it could be. See, have I succeeded in scrambling your brain this morning? So, do we have some level of clarity on this? If you've got a question, ask it. I'm not in a hurry. If I don't finish this today, it's okay. How you guys doing on Zoom? I don't hear any snoring, so. Can you guys still hear me?
Yep.
Okay. All right.
Wait, Dawn, for the exam, are the concentrations of the ions, are they going to be given to us and then we just have to plug them into the equation, or how would we find that?
I'm totally going to ask you to do an experiment and measure them. That's a joke. Yeah, if I need you to know ion concentrations, I will make sure that they are available to you in one way or another. How's that?